Okay, so hello everyone, my name is Abhishek Pandey and welcome to the week 3 session. Okay, so problems will be on the following content. So I will briefly recall all these contents and we will see some problems based upon those things. Okay, and if you have any doubt, feel free to ask me at any time. Okay, so first, yes,
Sir, lecture 2 faces some doubts. Sir. There are some doubts in lecture 2.
week 2. Just tell me, it was on isometries and other things, no?
No, sir, power series and Abbott's theorem.
Content is different or what? Week 2 or week 3?
Week 3.
Week 3 na, so week 3 I will, yeah, so week 3 is on the power series, so that's why I'm going to present.
Okay.
Yeah, okay, so we'll just recall the concept of differentiability. So suppose you have a domain in C, omega, so domain means open connected subset of C, and f be a function. We say that f is differentiable at z naught provided this limit should exist. Okay, limit z tends to z naught, fz minus fz upon z minus z naught. And if f is differentiable at z naught, we denote the derivative of f at z naught by f dash z naught. Okay. Okay. So basically, differentiability you can define in one different way also. That is also equivalent to this definition. That is known as the linear approximation of the function. So it is like, let omega be a domain in C and f such that omega to C be a differentiable function, and take a point z naught belongs to omega. So f is differentiable at z naught and f dash at z naught equals to C. It means that there exists a linear transformation from C to C such that limit z tends to z naught, this modulus value fz minus f of z naught minus L of z minus z naught upon modulus value of z minus z naught, this should go to 0. Okay. Yeah. Okay, so I think this is clear to everyone how we linearly approximate a differentiable function. So, yeah, fine. So how does the proof works? So let f be a differentiable at z naught, then f dash z naught denoted by this one, and consider the linear transformation defined as this one. Okay. Now you can see that this limit z tends to z naught of this quantity is nothing but limit z tends to z naught fz minus f of z naught minus f dash z naught into z minus z naught, and this is equals to 0. Why? Because f is differentiable. Okay, and conversely also you can check this one. So basically what you are getting is that you are getting an alternate description of differentiability that involves the notion of linear approximation. Okay, this is important because once you define the notion of differentiability in higher dimension, you need this linear approximation. Okay, that we will discuss in the later stage. That will be discussed in R differentiability and C differentiability. Okay. Okay, so basically it says that in other terms, if you want to define differentiability, so f is said to be differentiable at z naught if there exists a complex number c with the property that fz can be represented as like this. Okay, where what is e? E is a function satisfying this quantity. Okay. Now once you have this one, if you define like this, a function capital Az equals to f of z naught plus c into z minus z naught, this defines a linear function of z that approximates f up to an error Ez. Okay, yeah, is it clear? That's the basic thing. Fine. So differentiability implies continuity. It's like proof is easy. some differentiation rules we have. I will not repeat those things. It is there in the notes. You can go through. Okay, so chain rule is important. Let f such that u to c and g such that omega to c be functions such that fu is contained in omega. If f is differentiable at z naught and g is differentiable at w naught, then composition is differentiable at z naught, and the differentiability of composition is defined at g dash f of z naught and f dash z naught. Okay. Now this g dash f of z naught is defined because this f of u is contained in this one. Okay. Okay, so let us see the first problem. So calculate derivative of s dash z where h of z is nothing but this one, z square minus 1 upon z square plus 1 to the whole power 10. So note that hz is nothing but a composition of two functions g and f, where gz is z to the power 10 and fz is equals to z square minus 1 and z upon z square plus 1. Now h dash z is nothing but g dash of f of z by the chain rule. This is chain rule into f dash z. Now this is just a calculation. Okay. Okay, so what do we mean by a holomorphic function? Okay, so let u be a domain and f such that u to c be a function. F is said to be holomorphic at the point z naught if there exists a neighborhood of z naught, okay, which is contained in the domain u, which is contained in the domain u of z naught, such that f is differentiable at every point of n. Okay, means you take any point z naught, there should exist a neighborhood. In that neighborhood, f should be differentiable at every point of that neighborhood. So obviously we say that if we say that f is holomorphic in this whole domain u if it is holomorphic at every point of u. So basically holomorphicity is a, you see that if a function is holomorphic at z naught, it means there exists a neighborhood n, okay, in which it is differentiable. So basically it means that f is also f is basically holomorphic in this neighborhood also. Okay, so holomorphicity is a kind of property in a neighborhood, okay, in an open set. Okay, so a holomorphic function from C to C is called entire function. Means a function f, uh, a function is said to be entire if it is differentiable at every point of C, complex plane. Okay, so you see, we will now look at a Cauchy-Riemann equations. So suppose f is differentiable at z naught. Let us denote z naught as x naught plus I y naught. So what would be the derivative of f at z naught? It is nothing but limit x tends to x naught, f of x plus I y naught minus f of x naught plus I y naught upon x minus x naught. Okay, like this definition I have written somewhere, I guess. It is sometimes convenient to use that thing. Yeah, this one. Okay. Yeah. So this will be nothing but limit x tends to x naught. This is nothing but f of x comma y naught. You can just consider it is in R2 and minus f of x naught comma y naught upon x minus x naught. Now this you can write it as uh, let us say fz is u x comma y plus I v of x comma y. Then you can write it as limit x tends to x naught u of x comma y naught plus I of v of x comma y naught. Okay, this f of x comma y naught is there minus u of x naught comma y naught plus I v of x comma y x naught comma y naught upon x minus x naught. Now you can just take real part one side, imaginary part one side. So it will be limit x tends to x naught u of x comma y naught and minus u of x naught comma y naught upon x minus x naught. Okay, and plus I limit x tends to x naught, you will get this quantity. Now this limit exists. Why? Can you tell me? So this limit exists because we are already assuming that f is differentiable at z naught. Okay. So and what is this if this limit exists? This is nothing but partial derivative of u with respect to x. Okay, and this is nothing but partial derivative of v with respect to x. So basically, if f is differentiable at z naught, you can basically write f dash z naught is nothing but ux at z naught plus I v at z naught. Is it fine?
Yes.
Yeah. So this is kind of a proof of this one. Okay. Now, and and what would be the yes, yes Subha? Do you have any question? Yeah. Okay. So basically, the partial derivative of f with respect to x is nothing but this one only. Okay, and this exists, and f dash z naught satisfies this one. Okay. Similarly, if you set z is equals to x naught plus iy and allow y tends to 0, we arrive at f dash z naught is nothing but vy plus minus iuy. This tells us that the partial derivative fy this also exists. So basically, and f dash z naught is nothing but minus I fy at z naught. Okay. Now f dash z naught is this one vy z naught minus I uy z naught, and also f dash z naught is this one. So now we will compare these two. So imaginary part and real part will be equal. So from there we will get this one. Okay. ux is equals to vy and vy is equals to minus ux, and this is what Cauchy-Riemann equation is. So what we have, and this equation is known as Cauchy-Riemann equation. So what we have just saw that if f is differentiable, it satisfies CR equation at that point, isn't it? Okay. So 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 to write it in terms of definition, a complex valued function is said to satisfy CR equation at z naught if this holds. So if a function f is differentiable at z naught, then it satisfies CR equation at z naught. Okay, by above argument. So basically, the CR equation is necessary for differentiability, but obviously it is not sufficient. Obviously, CR equation is not sufficient for the differentiability. I mean, you can see a lot of examples and create on your own. Is it clear up to this? Is it clear?
Yes.
Yeah. Okay. Now we will see the sufficient condition for differentiability. So let omega subset of C be a domain and f such that omega to C be a function and z not belongs to omega. Suppose that the partial derivatives ux, uy, vx and vy exist in a neighborhood of z naught, and if each of these partial derivative is continuous at z naught and satisfies the CR equation at z naught, then f is differentiable at z naught. Okay. So it means that if you have a CR equation and these partial derivatives are continuous in at that point z naught and exist in a neighborhood of that point z naught. Okay. So just remember these two are important conditions. It has to exist in a neighborhood of z naught and it has to be continuous at the point z naught. Okay. Then f will be differentiable. This is kind of well known result. Okay. Okay, I will just write a notation. So f belongs to ck omega. It means that if all possible partial derivatives fx, fy, fxx, fyy up to the order k. Okay, so up to the order k, whatever kind of partial derivatives you can have, if those partial derivatives exist in omega and continuous in omega, we say that f belongs to this class ck omega. So let f belongs to C1 omega. If f satisfies CR equation at every point in omega, then f is holomorphic in omega. Isn't it? Whether this corollary is clear? So basically, f belongs to C1 means what? Fx, Fy, these are continuous. Isn't it? And if
Yes, it's clear.
yeah, if fx fy continuous, then means ux uy are continuous. These things are continuous, and hence by this theorem you have the differentiability. Okay. So, so a C1 is smooth. This is also called CK smooth function. So if C1 is smooth function, satisfies CR equation at every point in omega, then F is holomorphic in omega. Okay. Just remember that here I am writing F is holomorphic in omega, not just differentiable at some point. This is something else I am writing. Okay, because it satisfies CR equation at every point in omega.
Hello, sir.
Yeah, hello.
Sir, will you provide this PDF?
Yeah, I will. Yeah, that will be there. Some link will be with you, na, with you guys. Yeah, on that. Yeah, in that Google Drive, this PDF will be there. Yeah. Okay. Now this is an important concept: R differentiability and C differentiability. So just remember that whatever I have mentioned here earlier, this definition of differentiability, this is nothing but this is a notion of C differentiable function, means complex differentiable function. Okay. I hope you guys are aware of with this thing. R linear map and C linear map. That was the content of, I guess, week one. No, no, week two. R linear and C linear map was the content of week one, week two, isn't it? So that we will use here. Okay. So for this, we just need to recall what we mean by a differentiable of a function in R2. Okay. So let U be an open set in R2 and F such that U2 R2 be a function. F is said to be differentiable at Z naught. Okay. So this differentiable at Z naught, just recall the definition of differentiability in several variable, in several real variable. So f is said to be differentiable at z naught if there is a linear transformation L such that R2 to R2 such that this limit goes to 0. This is the way we define differentiability in higher dimension, isn't it? Here mod
Yeah,
z, yeah. So here norm of z, or you can just write mod of z, is nothing but under root x square minus y square. Okay. Now let f is a function from a domain in C to C. Now this can be seen as a function like this, isn't it? Because topology are same, C and R2. Okay, so you can just see C as R2 and this function you can consider as this one. Okay, where omega is a domain in C and let Z not belongs to omega. So basically f can be considered as a function f such that omega to R2 by taking Z is equals to x plus y iy as x comma y. Okay. So now f is said to be differentiable in the real sense. Now I am talking about this function. Okay, f such that omega to c. So f is said to be differentiable in the real sense at z naught, or in short, r differentiable at z naught if it is differentiable in the sense of this star definition. This is star. Okay, at z naught. Is it clear? Whether definition of r differentiability is clear?
yes, clear.
Okay. So okay, so this theorem is important. So suppose a function, yeah. Suppose that a function f is defined in an open subset U of C. Here, just note that I am not using connectedness because in the proof connectedness is not required. But just to make things not more complicated, we use the assumption of connectedness, open and connected set. So okay, so suppose that a function is defined in an open subset U of C, and that the partial derivative exists everywhere in U. If each of the partial derivative is continuous at z naught belongs to u, then f is R differentiable at z naught. Okay, is it clear? This is statement. I hope it will be clear.
Yes, sir. Repeat once more.
Yeah, so it says that if like you just recall the sufficient condition for differentiability in R2. If the partial derivative exists everywhere in U, and if each partial derivative is continuous at this point, f will be differentiable at that point, isn't it?
Yes.
Yeah. So it means that f is R differentiable at that point z naught. Is it clear? Okay. And furthermore, fz can be written as f of z is equals to f of z naught plus this partial derivative. So this del is nothing but del by del z. Okay, and this del bar is nothing but del by del z bar. I will come to this one later on. Del of f of z naught. So this is nothing but del of del z of f at the point z naught. Okay, this is the meaning of this one. Okay, z minus z naught and del bar of f at z naught into z bar minus z naught bar plus e to the e of z. Okay. Okay, fine. Okay, yeah, and where E satisfies this equation. So this is limit z tends to z naught. Modulus of E of z upon z minus z naught is equals to 0. Okay. Now if you write f of z as this one, and you take L of z minus z naught as A of z minus z naught plus B of z bar minus z naught bar, where A is nothing but this one and B is nothing but this one. So what is your L? L is nothing but what? L is a R linear map, isn't it? What is R linear map? So every R linear map from C to C is of this form. R linear map means it is a function. It is a function from C to C, but it is linear when you consider C as a vector space over R. Is it clear? Whether R linear map is clear to everyone?
Yes.
Yeah. So basically, R linear.
Repeat the
Okay. So
repeat the concept of harmonious symmetry.
okay. So R linear.
Coherence containing many factors.
Okay, I think it is okay. Okay, anyhow, I will just. Anyhow, I have uploaded this week 2 content on the YouTube. Okay, you can just see. Anyhow, I will just repeat now. So consider a map from T such that C to C. Now C can be considered as a vector space over R as well as over C, isn't it? Now if this T is a linear map, when we consider C as a vector space over R, then we call this map as R linear map. And if this is a linear map, when we consider C as a vector space over C, this is called the C linear map. Okay. So basically every R linear map is of this form. This like this you can see as an exercise. Week 2 also lecture notes I have uploaded uh, on the Google Drive. You can just go and see. Uh, so every R linear map is of this form, AZ plus BZ bar, and every C linear map is of this form, lambda Z. So basically you can check that this lambda Z kind of map are basically a linear map. They are basically linear transformation from C to C when you consider C as a vector space over C. Is it clear?
Yes, now it's clear.
Yeah. Okay. So basically if you see that, So in this definition, if you see that if you just take this one, fz is equals to this one, okay, so L of z minus z naught is nothing but this one. So basically, which is nothing but a R linear map. Okay. So means once you define the R differentiability of a complex valued function, this thing is nothing but a linear transformation taking C as a vector space over R. Means these are the R linear map. Okay. Just wait. Okay. So means what? Like so the only so the what is the difference between R linear map? So you take a you take a complex valued function. What is the difference between R differentiability and C differentiability? So in the R differentiability, you will get this map, this R linear map, and in the C differentiability, you will just get this as a C linear map. That is nothing but some a C into constant of f dash z naught. Okay. Basically, if f is C differentiable, means this quantity will be 0, isn't it? If f is C differentiable. Is it clear? But so this will become from Cauchy-Riemann equation. This delta bar of f of z naught will be 0, isn't it? Where is that? Yeah, ux vy and uy equals to minus vx. Oh wait, I haven't tell what do you mean. How do we define delta bar? Okay, so here is some notation. This should come first, but anyhow. So f is equals to u plus iv, fz is equals to uz plus ivz, or you can write it as this one. Now what would be f, partial derivative of f with respect to x? It is nothing but ux plus ivx. Okay, and what is the derivative of f with respect to y? It is nothing but uy plus ivy. Okay, now you take x is equals to z plus z bar by 2 and y is equals to z minus z bar by 2y. Okay, so basically what is x? F is, you can consider as this one. F is from function of x comma y, and x comma y are function of basically z and z bar. Now we want to calculate the partial derivative of f with respect to z. So you calculate the partial derivative of f with respect to x and then the partial derivative of x with respect to z, isn't it? So del f by del z is nothing but del f by del x and del x by del z plus del f by del y into del y by del z. So this is so this is how we calculate the partial derivative of f with respect to z, del f by del z. Okay. What is this? This will come as 1 by 2 fx minus I fy, which will come as this one. Is it clear? Okay. So, and similarly, you can see that del f by del z bar is nothing but this one, 1 by 2 ux minus vy plus I vx plus uy. Now, now if f satisfies the CR equation, what will be this del f by del z bar? This will be 0, isn't it? Because see, in CR equation ux is equals to vy, so this quantity will be 0, and vx is equals to minus uy, so this quantity will be 0, isn't it? Is it clear?
Yes, it's clear.
Okay, just wait a minute. Okay, so since f is R differentiable at z naught, and so it is R differentiable at z naught, so there exists a R linear map, okay, which is nothing but of the form L of z is equals to az plus bz bar. Okay, so if you want to write the determinant form of L, this will be the determinant. the matrix form of this linear transformation will be this one. Okay. Now, if you calculate the determinant of this matrix form, it is nothing but mod A square minus mod B square. Now, what is this one? So, this is known as the Jacobian of f. Okay. So, mod what is this A? A, we have already seen that it is nothing but del f, which is nothing but del z of f, which is nothing but del f by del z. So, we'll get this one minus this one. Whether this one is clear? You just remember the form of this Jacobian of f. Okay. So I
Yes, it's clear.
yeah. Okay, so we'll see our first problem. Uh, the problem is visible. You can see this problem
Yeah,
now.
visible.
Yeah, okay.
Visible.
So let omega be an open connected subset of C and f be a holomorphic on omega. Suppose f is equals to u plus iv, where u is a real part of f and b is an imaginary part of f. Which of the following statements are true? The Cauchy-Riemann equation says that ux is equals to minus vy and uy is equals to vx. So is it true?
No, it's not.
Yeah. So this is not true. Oh, sorry. I have already written which is true, which is not true. Okay. Anyhow. Okay. So the function f conjugate of f is always holomorphic on omega. Is it true always? So like if you take so if you take fz is equals to z, z is holomorphic, but z bar is not holomorphic, isn't it?
Yes, that's not.
Yeah. So, okay. So now what would be the condition on f this conjugate function to be holomorphic? So the function f bar is holomorphic on omega if and only if this ux is equals to minus vy and uy is equals to vx. Let us see this one. Okay. So option 1 is false. Okay. So let fz is equals to this one is holomorphic on omega. Now f bar z is nothing but this one. So suppose this thing is holomorphic. So means f bar will satisfy the Cauchy-Riemann equation. Okay. Is it clear? So first we will use the Cauchy-Riemann equation, CR equation of f, which will denote it as ux is equals to vy and uy is equals to minus vx. Also using CR equation of f bar, we get ux is equals to minus vy and uy equals to vx. Now if you combine equation 1 and 2, you will get vy0, vx0, ux0, uy0, which gives that this derivative of f is 0 and omega is connected, means f is constant. Thus we get that f and f bar are both holomorphic if and only if f is constant. Is it clear?
Yes, clear.
Yeah. Okay. So this is also clear. If f bar is also if f bar is also holomorphic, then ux and uy are identically 0. Okay. If the function f
Yes,
bar
they
is,
are.
yeah, so the all three are like automatically it satisfies for a
Yes.
constant function. Yeah. Okay. So suppose that f is a holomorphic function defined. So this is another problem. Suppose that f is a holomorphic function defined on a domain omega such that the image of f is contained in a straight line C. Then f is identically equal to 0. This is what we need to see. Okay. So let f such that omega to C is be holomorphic. Sorry. Let f such that omega to C be a holomorphic function. If f omega is contained in a line, okay, then f is a constant function. So let the equation of the line be mx plus c, y equals to mx plus c. Now what is f of x plus iy? Let us say f of x plus iy is nothing but this one. Since f of omega is contained in line, we can write v of x comma y as what? See, y is equals to mx plus c. So we can write this y part, this v, okay, as mux plus c, isn't it? Basically,
Yes.
yeah. So now f of x plus y is nothing but u of x comma y plus I of this one. So we get Vx is equals to Mux and Vy is equals to Muy. Okay. But since f is holomorphic in omega, so it satisfies CR equation. So it means that Ux is equals to Vy and Vy is equals to minus Vx. Okay. Now what is Vy? This is nothing but M of Uy. So Ux is equals to M of Uy and Uy is equals to minus M of Ux. Is it clear?
Yes, clear.
Okay. Now what does it mean? So what would be Ux? Ux is equals to what? Ux is equals to, wait a minute. Sorry, what is Uy? Yeah, so Muy and just wait a minute. So Muy. Yeah, so Ux is equals to Muy and Uy is nothing but minus Mux. So Ux is what? Minus M square Ux, isn't it? So this is 1 plus M square into Ux. This is always a positive quantity. Okay. So Ux has to be 0. This implies Uy 0 and Vx is equals to 0 and Vy equals to 0. This implies derivative of f at z is 0 and since omega is a domain, f will be constant. Is it clear? Huh.
Yes.
Okay, so first option is not correct. Okay, I mean, I mean, wait a minute. Yeah. So first option is saying about that f is identically equal to 0. It can be constant. Okay, need not be always identically equal to 0. So first option is not correct. Second option is correct. Then f is constant. Okay. Now third option is if f is a holomorphic function in a domain such that mod f is constant, then f is also constant. Okay. Let's see this one. So let f says that omega 2r is holomorphic such that mod of f of z is equals to k for every z belongs to omega. Okay. If k is 0, we are done. Okay, because f will be 0. So f will be constant. So let us assume that k is not equals to 0. It implies there there are some point z belongs to omega where f of z is non-zero, isn't it?
Yes.
Yeah. Now modulus of f of z square is what? K square. What is modulus of f of z square? It is nothing but f of z into f of z whole bar, isn't it? So what is now f bar z is what? K square upon f of z. Okay. And now f bar is also holomorphic, which means that f is constant. Earlier we have seen if f and f bar is holomorphic, then f has to be constant. Is it clear?
Yes.
Just wait. Okay, so some problem is there with my camera. Yeah. Now, what is the fourth option? Fourth option is asking if f of x plus iy is equals to x into y, then f satisfies CR equation at the point z is equals to 0. Okay, let us see this one. So let us take f of z is equals to x into y. So now compare. Assume that f of z is equals to ux. So fz can be written as u of x comma y plus I v of x comma y. So u of x comma y is nothing but x into y, and v of x comma y is 0. Okay. Now you can calculate ux, vx, uy, vy. Okay. So at x comma y 0, so at x comma y equals to 0 comma 0, it is clear that f satisfies CR equation, isn't it?
Yeah.
Okay. Now obviously second option is not correct. That f of x comma y, this x into y is holomorphic on the unit disk. Okay. You can just take points where this CR equation is not satisfied. Okay. Okay. Is it fine? Okay.
Yes, sir.
Okay. So now we will talk about power series. So just remember, while I'm discussing the problem session, uh, for the later stage, once uh, till the Cauchy integral formula, I will use two notions. One is holomorphic and one is analyticity. So holomorphic I have already defined, means it is differentiable at that point, sorry, in a neighborhood of that point. Now I'm going to define the analyticity of a function. Although they both are equivalent, but to prove the one part, we need the Cauchy integral formula that we will see later. They both are equivalent, holomorphic and analytic function, but the historical development is different. So to define the analytic function, we need the power series expansion. So let us first see what power series is. Is it clear whatever I have said?
Yes, sir. Clear, sir.
Okay. So let an belongs to C for every n greater than equals to let me write it down. N is greater than equals to 1. You can take n equals to 0 also, it doesn't matter. So series an converges to z if and only if, this is the definition of this one. Okay, it means that if this thing is, this is the partial sum converges. Is it clear?
Yes, sir.
And this is converges absolutely if this is convergent. Let us recall the concept of, should we should I recall this one, limit inferior, limit superior? I think it is well known to you guys. It is there in the notes. If you like, once you are recalling all these things, you can recall here.
Okay, sir.
Yeah. This is the property of limit inferior and superior, because obviously the when we define the radius of convergence, we use this concept, limit superior and inferior. Okay, so a power series centered at z naught is an infinite series of this form. Summation n equals to 0 to infinity a n of z minus z naught to the power n. Okay. Now consider the series, this one. This is the well-known series of 1 upon 1 minus z. Okay. So for a given power series, this one, define the number r as this one. This is known as the radius of convergence. Then z minus z naught is less than equal for this region, for this domain. What we this is the ball centered at z naught and radius r. This series converges absolutely. Okay. And if mod z is greater than mod z minus z naught is greater than r, this series diverges. we don't know what happens on the radius of convergence, sorry, circle of convergence. This one we don't know. Okay, in general there is no statement for the convergence on this one. And if you take any r less than capital R, this series converges uniformly. Okay, uniform convergence you guys know. You just take this series as uh, f and z, and then study the uniform convergence of this function f and z. Okay. Okay. So there, so here we are taking the limit superior of this one, mod a n to the power 1 by n. This is the well-known formula. But if this limit exists, mod of a n upon a n plus 1, then this becomes the radius of convergence. Okay. For an example, you can take these things. Okay. Okay. So if you take a power series, consider it as a function fz. Okay. Uh, Suppose this has radius of convergence r positive, then for each k greater than equals to 1, this also has r, radius of convergence as r. So this will be nothing but the nth derivative of, sorry, kth derivative of this one, isn't it?
Yes.
So it means that this is infinitely differentiable on this ball. And furthermore, fkz is given by the series 1. So this is nothing but the kth derivative of f. So what does it mean? If you have a power series, that is, if you represent this power series of function, okay, I will tell it later. Okay, so this is the formula for an. Okay, just remember this theorem. Okay, what do you mean by analytic function? So we say that f is analytic at a point z belongs to omega. Just wait a minute. Let me see the camera. Okay, so we say that f such that omega to c is analytic as z belongs to omega if it can be represented by a convergent power series expansion in some neighborhood of z naught. Means fz can be written as this one. So let us use this notation. So f of zeta is nothing but summation k equals to 0 to infinity ak zeta minus z to the power k. Okay, is it clear? So in this case, we say that f is analytic at this point z. We say that f is analytic in the domain U if it is analytic at every point z belongs to U. Now, once you see this f, once you define analytic function, now you can see by this previous theorem, this theorem star, that every analytic function is basically holomorphic, isn't it?
Yes.
Okay. So basically every analytic function is, so in view of theorem star, wait, just let me write it down. So in view of theorem star, we have the following corollary, which says that if f is analytic as z, then f is holomorphic at z. Converse is also true, means holomorphic implies analyticity. This we will prove when we study the Cauchy integral formula. Okay. Up to this, everything is fine. Do you have any doubt?
Yes, sir. It's fine.
Okay. Okay. Let us see some problems. Okay. So suppose fz is a polynomial in the complex variable z of degree n greater than equals to 0. Which of the following are true? F has a power series expansion around every point W belongs to C. Okay. So you have a polynomial, this one, fz is equals to a naught plus a1 z plus and so on a n z to the power n is a polynomial. Compare f with the following summation. So I am defining this one, summation a n z to the power n, where aj is equals to 0 for every j greater than equals to n plus 1. Okay. What would be the radius of convergence of this series? Where an is visible. Okay, so let me write it down. And basically here your aj is equals to this an when j is equals to 1 to n. Okay, so az is equals to a. Oh, sorry. Aj is equals to basically nothing but aj only, where j is equals to 1 to n. Okay, so a1 is nothing but a1, this a1, and so on. So what would be the radius of convergence of this one? This limit superior of mod of an to the power 1 by n will be nothing but 0, isn't it? Is it clear? Yeah, so thus f is entire and hence it has a power series expansion around every point w belongs to C. Okay. This is also true. The radius of convergence of power series of f around any point w belongs to C is infinity. That's what we have just proved now. There are only finitely many w belongs to C such that a naught is equals to 0 in the power series expansion of f around w. What is this third one? So fz is equals to this one. What is this basically? What is this a naught? A naught is what? A naught is f of 0, isn't it?
Yeah.
Yeah. So you can have only, wait a minute. Just wait a minute. Yeah. So suppose this is a polynomial and the power series expansion of f around w. So what will be the power series expansion of f around w? This will be the power series expansion. Okay. What is a naught? F of w naught, isn't it? Oh, sorry, I have to write this a n. This would be a n. Okay. So a naught is nothing but f of w naught. So w naught is a root of a polynomial, and polynomial have only, so polynomial has only finitely many roots, isn't it? So there will be finitely many w belongs to C only. Is it clear?
Yeah.
What is the fourth option? Since f is a polynomial of degree n, therefore f always remain a polynomial of degree n when we write its power series expansion around any point w belongs to C. Okay. So there are only finitely many w belongs to C such that a of n plus 2 is not equal to 0 in the power series expansion of f around w. Okay. So power series expansion of f around any point w will again be a polynomial of degree n. So this a n plus 2 is what? What will be this a n plus 2? Anyone? Whether this statement is clear, D1, I think some problem is there in this one. Anyhow, this will be, I think some problem is there in this statement, because f is again going to be a polynomial of degree n. Okay, so up to n only terms will be there. Other than that, for n greater, so other than that it will be 0. So it will be 0, an plus 2 will be 0 for any w in C, isn't it?
Yes, sir, clear.
Yeah. Okay, now suppose that okay, suppose that f has all its roots in C and does not have any repeated roots, then the number of w belongs to C such that the constant term of the power series and w equals to 0 is n. Let us see this one. This is a nice one. So suppose f has all its roots in C and does not have repeated roots. Since f is a polynomial of degree n, so it has n roots, say alpha 1, alpha 2, and alpha n. Consider this set S. This set S is w belongs to C such that constant term of the power series of f around w equals to 0. Okay. So what is S? So if constant term of the power series of f around w equals to 0, what does it mean? Basically an z minus w to the power n. What would be the constant term? F of w, isn't it? F of w is the constant term,
Yes,
which is 0. So the set S is what? Number of zeros of the polynomial f, isn't it? Is it clear?
yes, yes.
So f, and hence the cardinality of S will be n only. So this option is also correct. Okay. Now let us see the next one. Okay, so the expression of this polynomial is this: fz is equals to 125 z per cube, and this z square, this into z minus this constant term. Constant term in the power series expansion of f about the point 4i is what? Mm-hmm. Hello?
Yes,
So what would be the constant term around f of f about the point 4i?
let's calculate.
So so
The value of y
so constant term will be nothing but f of, so this is your f of z around 4i. So what would be the constant term? So this is nothing but a naught, sorry, summation an z minus 4i to the power n. So if you take f of z is equals to 4i, so f of 4i will be the constant term of f about the point 4i. Okay, let me just see. Then the constant term in the power series expansion of f about the point 4i, It is f of z is nothing but, let me see, f of z is nothing but, this is summation an, let's say bn z minus 4I to the power n is equals to 0 to infinity. So this is your a naught plus a1 into z minus 4I, okay, plus a2 into z minus 4I square, okay. So what would be the constant term? So when you take, so what would, so how you will get this constant term? If you take f of 4I, what you will get? A naught. So this is a constant term, okay, which is which is nothing but non-zero, okay. Here it is non-zero. Is it clear?
Yes.
Hmm. Okay, so this is also not correct. Let us see this problem. So suppose f is a power series around 0 given by this one. Just wait a minute. Okay, so suppose that f is a power series around 0 given by this one, okay, with a positive radius of convergence. Which of the following statement are true? So if ai is equals to aj for all ij belongs to this one, then f is uniquely determined by f of 0. Let us see this one. So fz is nothing but this one, okay. What does it mean? F of 0 is equals to a naught, and radius of convergence is r, which is positive. If ai is equals to aj for every ij, okay, then since f of 0 is equals to a naught, so what would be f of z? Mhm. What does it mean? F is uniquely determined by f of 0. Means you can basically, in terms of f of 0, you can write all these, this f. You don't need any other constants. Okay. So f of 0 is basically a naught, okay, and wait a minute. Yeah, exactly. So f of z is nothing but a naught plus summation this one, a naught z to the power n, and f of 0 is a naught. So what would be f of z? At the place of a naught, you can write f of 0. Okay. Sorry. Sorry. So at the place of a naught, you can write f of 0. Means fz is uniquely determined the only value of f of 0. Okay. Means you need, you don't need the other constant. Is it clear?
Yes.
Okay. I mean, uniqueness you can check. This is determined by f of 0. Uniqueness you can check. If it is determined by some other quantity, you can just subtract it and you will again get f of 0. If ai is equals to az for any 2I comma j and a naught is equals to non-zero, then the radius of convergence of their power series is 1. Okay, this is easy. So if ai is equals to az for any 2I comma j and a naught is equals to non-zero, so an is equals to a naught for n greater than equals to 0, isn't it?
Yes.
Yeah. So now fz is equals to a naught plus summation this one a naught z to the power n. Now this is nothing but r is equals to 1. This lim sup of a n will be 1. Is it clear? Okay. If an is equals to this one, sorry, if an is equals to n plus 1 into an plus 1, then the derivative of f is itself in the region of convergence of the power series ever. Just see this one. C. So let an is equals to this one. What is a naught? A naught is a1, a1 is 2a2, a2 is 3a3. So basically a naught, so fz is a naught plus uh, an z to the power n. What is derivative of this power series? That will be n an z to the power n minus 1, isn't it? Now what is this one? So if you start it from 0, okay, and you take let us say n minus 1, you take capital N, you will run through this one. Okay, wait a minute. So here if you take n equals to 1, what you will get? A1. Okay, and if you take here n equals to 0, what you will get? A1, isn't it? So these two power series are same, this and this. Is it clear? I mean the coefficients are same. So what is this one now? This one is nothing but this one, since n plus 1 into an plus 1 is nothing but an. So the derivative of f is again that's the same power series. Okay, is it clear? So this is fine. Now let us see the next one. Define gz is equals to a naught square plus an square into z to the power n. Okay, if the radius of convergence of f is 2, then the radius of convergence is of g is under root 2. Let us see this one. So let gz is equals to this one. Gz is defined as this one. Okay, so gz is nothing but summation n equals to 0 to infinity an square to the power zn. Let us write it down. N equals 0 to infinity bn into z to the power. So what will be the radius of convergence of g? It will be 1 upon limit sup of bn to the power 1 by n. What is bn? It is an square. So it will be limit sup of modulus of an square to the an square to the power 1 by n, which is nothing but 1 upon limit sup of mod an to the power 1 by n to the whole square. What is the what is this quantity? What is this one?
What?
No, no. This is the radius of convergence of what? F, na?
Yes.
Yeah. So this is the ROC of F. So what is ROC of F? It is capital R, positive. It is written somewhere. So so basically what we get? ROC of G is nothing but ROC of F whole square, isn't it?
Yes.
So if ROC of F is 2, what will be the ROC of G? It will be 4. It is R square. So if so ROC of G is nothing but R square. If R is 2, ROC of G is 4. So the given option is not correct. Okay, so this is not correct. It is saying that if ROC of F is 2, then the ROC of G is under root 2. It should be 4. Okay. If the radius of convergence equals to 1, then the positive expansion of F around the point 1 by 2 has also the radius of convergence equals to 1. Let us see this one. This is also important thing. Okay. So take Fz is equals to Z to the power n. 1 upon 1 minus Z. What is the radius of convergence of F? It is 1. So now if you take the radius of convergence of f around this point 1 by 2, it can go at most 1 by 2, isn't it? Which is not equals to 1. Is it clear?
Yeah.
Yeah. So for the same thing, if you take the radius of convergence, for the same thing, if you take the power series around some different point, ROC may change. Okay. So for this f at the point 0, if you take the expansion, the ROC will be 1. If you take that at the point 1 by 2, ROC can't be 1. Okay. So now let fz is equals to 2 plus summation this one, and the ROC of f around the point 7 by 3 is r. Then what is 3r? Okay. So let fz is equals to this one. So you just take 3 common, and it will be 3 to the power n. So the an, so this is, let us say this is an. So this is your an. Okay. Now what is this limit? Whether this limit exists or not. So this limit is nothing but 1 by 3. So what would be the radius of convergence? It will be 1 by 3. Okay. So 3r is equals to 1. Is it clear? This is just a calculation. This one is clear, na?
Yeah.
Okay. Let p be a polynomial with positive coefficients. Then the radius of convergence of the following power series is what? So p is a polynomial with constant positive coefficients. So let pz is nothing but this one. This is the polynomial where all this ak is positive. Okay. Consider fz is equals to this one. This thing we need to consider. Okay. So compare this fz in this expression. So what is your bn? Bn is nothing but pn upon n factorial if n is equals to m factorial for some m. Otherwise, it is 0. Is it clear? The way it is defined. Because you need to consider this one also. N factorial is here. It is not just z to the power n. It is n factorial. Okay. So let me just write it down in the proper way. Sorry. So this one. Okay. So this fz is nothing but 10 plus summation n equals to 1 to infinity Pn upon n factorial upon z to the power n. So if you just see this one, this is what 10 plus summation. Wait, so if you take n equals to 1, what will be this one? So it will be p of 1 into z. Okay. If you take n equals to 2, okay, so what is there? What is 2 factorial? It is again square. So p of 2 upon 2 into z square plus, if you take 3, what is 3 factorial? It is coming 6. So it is p3 upon 6 into z to the power 6. Now in between terms, like it is 0 into z cube plus 0 into z4 plus 0 into z5. Is it clear?
Yeah.
Yes, sir. So these terms are 0. So if we want to define fz in like this one, summation n equals to 0 to infinity bn z to the power n. Okay. Here just see, this is z to the power n. So what would be b naught? It will be 10. What would be b1? It is p1. b2 is what? P of 2 upon 2. b3 is what? 3. b4 is what? Oh, wait a minute, sorry. So b3 is what? 0. b4 is 0. b5 is 0. And again b6 is b6 is p3 upon 6. What does it mean? If you can represent these natural numbers in terms of some factorial, then you have some value of bn, otherwise it is 0. Like 3 cannot be written as the factorial of any natural number, isn't it?
Yes, sir. Yes.
4 cannot be written as the factorial of, and 5 cannot be written as the factorial. So these quantity will be 0. That's what I have written in general. So bn is nothing but pn upon n factorial if this n can be written as m factorial for some m and 0 otherwise. Okay, so what would be lim sup? It will be mod bn to the power 1 by n, which is nothing but 1 upon n. Wait a minute. So p of z is equals to 1 implies p of n is equals to 1 for every n, isn't it? Let's see. Just wait a minute. So p of n is equals to 1. How do we get this one? I think some extra condition is there. Anyhow, so wait a minute. P of z is equals to 1. Is it given somewhere? Okay, one extra condition is missing here. So p of n is equals to 1 for every n. It means that radius of convergence is nothing but lim sup of this quantity, which is 1 upon factorial n to the power 1 by n, which is nothing but 1. Is it clear now?
Yes, sir.
Yeah. So this will be 1. I think the next will be the last question. Yeah, this one is the last question. Okay, so which of the following statements are true? The function, this one, so it is e to the power z bar, then whole bar of this one is entire. So f is entire if and only if, okay, so let us prove this one. Let us prove this statement. So f is entire if and only if f z bar to the whole bar is entire. Okay, so let f is entire, then f can be written as a power series expansion around every point z belongs to C. Okay, just wait a minute. Just wait a minute. Hello, am I audible?
Now, sir.
I'm not audible. Hello, am I
Audible,
okay? Okay, fine.
sir. Audible.
Yeah, thank you. So, okay, so which of the following? Yeah, okay, yeah, so we want to prove this statement. So f is entire if and only if fz bar to the whole power bar is entire. So in particular, the expansion of f, since f is entire around z equals to 0, is nothing but fz is equals to this one, isn't it? Now what is fz bar? This is this one. And what is the whole power bar? This is this one. Now this bar thing we can just take inside the power series. So it will be like this one. Okay. Now this thing, let us say an bar is equal to cn. Okay. So what would be the this one? This will be nothing but modulus of Cn into z to the power n. It will be Cn bar modulus into z to the power n modulus. Cn bar modulus is what? Now you just take the modulus here. This will be Cn bar to the power z to the power. What is Cn bar? Cn bar is again An. Now An z to the power n. So means this thing converges absolutely. If and only if this is absolutely convergent. Thus, since fz is entire, therefore this is also entire. Is it clear?
Yeah.
Okay, next thing we have to verify this one. Sin z bar to the whole power bar is equals to minus sin z if and only if this thing is there. Okay. Okay, so let us see this one. These are just calculations now. So this thing you can write it as like this one. Sin z bar is also sin x minus iy. This you can write it as this one in the hyperbolic term, and you take the whole bar. Okay, so it will be plus sign will come here. And what is this one? Sin x plus iy. Is it clear? Yeah. And then you can just follow the easy computation. Similarly, for cos z is let cos z is equals to 0. So cos of x plus iy equals to 0, which is nothing but cos of x into cos hyperbolic of cos y minus I sin x hyperbolic of sin y. This will be this one. Just wait a minute. What is this? Okay, so this is 0 if and only if this plus sign is 0. And what is this one? This is cos of z bar is 0. So cos z is 0 if and only if this one is 0. So means this is also true. So these things are true. Now next thing is p is a non-constant polynomial with coefficient in the complex plane C. Is it visible? Yeah. Then p of e to the power z bar to the whole power bar is p of e to the power z. Let us see this one. So you take a polynomial z plus I. What is p of e to the power z? It is e to the power z plus I. Okay. Now what is e to the power z bar to the power whole bar? It is e to the power z bar plus I to the power whole bar. So this will be e to the power z dot to the power whole power bar minus iota. Okay. Now you can write e to the power z bar as e to the power x minus iy, which is nothing but e to the power x into e to the power minus iy to the whole power bar. Okay. And e to the power iy you can write like this one. Now what would be this a into b bar is nothing but you take this e to the power x, you multiply this one. So this will be e to the power x y minus I e to the power x sin y to the power whole bar minus iota. This will be e to the power x into cos y plus this plus sign will come because of this bar. This will be iota e to the power x into sin y minus iota. Now again you take e to the power x common. This will be cos y plus I sin y. What is this one? This is e to the power iy. So this is e to the power x into e to the power iy minus I. Now this is what? E to the power x into e to the power iy is again e to the power x plus iy. This is nothing but e to the power z. So we'll get e to the power z minus I, which is not equals to e to the power z plus I. Okay. So this thing is also not correct. Okay. Because p of e to the power z is what? E to the power z minus I. Okay. The way we have taken this one. Is it clear?
Yeah.
Okay.
Yes.
Now, now the next thing is the function gz. So the function gz is equals to f of z bar to the power whole bar is entire if f is entire. Let's see this one. Wait a minute. Okay, yeah, so this comes from this one only. F is entire if and only if this thing is entire. So suppose if f is entire, this will be entire, isn't it? So G will be entire.
Yes, sir.
Is it clear? So yeah, we are done with the today's assignment. Any doubt?
No, sir.
Okay. Subham, any doubt? Akanksha, any doubt?
But sir, the concept you cleared and assignment of it will be different. Is different.
Sorry?
Sir, assignment topics and today's class concept is different something.
It is same, na? Week third, this is the concept, now on the differentiability and power series.
No, it's only concept of power series and convergent of power series. And the main concept like Abel's theorem and other theorems for convergence and radius of convergence.
Yeah, radius of convergence I have covered. Maybe I have not done that much problem solve, like not that much problems. But these problems are from the previous assignment. I have not gone through the present assignment questions. Okay, anyhow, if I see anything I have missed, I will continue in the next class and then for the same thing. Is it fine?
Sir, there is
Uh-huh.
any class at 6 p.m. also?
3 to 5, yeah, yeah. One class will be from 5 to 7. One more PMRF is there from mathematics. He will take that class.
Sir, this is first class at 3 p.m.
Yeah, this is the first class. Actually, the problem is I was taking the class from. I forgot that my class is 3 to 5. I was taking the class from 7 to 9. So that is the problem. So now I remember that the class is from 3 to 5. So yeah, the first class is 3 to 5, and the second is from 5 to 7. But
Sir, second class will be at 6 to 8.
oh, is it 6 to 8? Okay, maybe. Okay, yeah, I think it is 6 to 8. Okay. For first week one and week two, I took the class at 7 to 9. That was the problem because I was like I really forgot that my class is at 3 to 5.
Okay,
So
sir.
yeah, so you guys can go through the like YouTube. I've uploaded the lectures of week one and week two, and also my notes for week one and week two in the Google Drive. You guys can go and check that one.
Sir, how I can access your Google Drive?
I think NPTEL has provided you some link na to access my materials.
Sir, no, your material.
Well,
It
still I not get your material.
you guys have link for this YouTube lectures?
No, sir.
You guys have registered for this NPTEL course, na?
Yes, sir. Yes,
Yeah.
sir.
Wait a minute.
So the link will be provided, I think, at least 3 4 days after.
Okay, maybe. So for week one and week two, whether they have provided you link?
Yes, sir. Lecture will be provided on YouTube, but lecture notes not provided.
Okay, anyhow, let me just write down the material link. So I'm writing the material link in the chat box. You guys can just copy it and save it.
Okay, thank you.
So this is the link for the material. I will just upload the week three lecture. Week one and week two are there. Is it fine? Hello? Is the H on? You got the link? Hello? Alok, Akanksha? Okay, fine. Okay, so I will close the session. So we'll meet in the next week session.